Hey everyone, welcome to our YouTube channel, and in this video we are going to discuss about a topic from applied electronics, that is Norton's theorem. So first I'll read out the statement, and right here we will solve a numerical based on the Norton's theorem. So any complex circuit network can be replaced by a parallel circuit consisting of an ideal current source and a resistance. So what does this mean? Basically, let us say if we have a system like this, wherein I draw a box like this, and inside this box there is a complex network of circuits, and let us say we have two terminals at the end, that is terminal A and terminal B. So what is going to happen is that we can convert this entire complex circuit network in a very simple format, where this would consist of an ideal current source, and in that ideal current source in parallel position would be one resistance. So this, in case what we have got here, this is known as the Norton's equivalent circuit. So what happens is that it basically converts a complex network circuit in a very simple format, in which there is one current source and there is one resistance. So this current source can be termed as IN, and this can be termed as Rn, where Rn denotes the resistance across the two terminals. Now there are certain rules or procedures for applying the Norton's theorem. So what are the rules that we are talking about, that while you want to apply the Norton's theorem, what is the rule? So let us take a very simple example. Let us say we have a situation where we have a circuit like this that carries a resistance R1, one voltage source like this, and we also have one more resistance, that is R2, and then this is connected to terminal A and terminal B respectively. Now let us say that there is a 12-volt battery here, positive and negative terminals. R1 and R2 have values of 3 ohm and 9 ohm. So the question is that we have to reduce this particular circuit in a Norton's equivalent circuit. So how do we do that? So the first step that we have to take is we have to disconnect all the load resistors, if there are, from the terminals A and B. Now fortunately the terminal A and B are technically open here, so what we can do is we can skip the first step. Now the second step is to put a short circuit across the terminals A and B of the given network. So for that we'll have to redraw the diagram. So let us redraw this diagram by short circuiting terminals A and B. So now this diagram would look like this. We have a resistance R1, then here we have a resistance R2, this is terminal A, this is terminal B, and the 12 volt battery is intact. Now as we have to short circuit this particular terminal A and B, so I'll join a wire here. So as soon as a wire here, a current ISC flows in this direction, because the current will come from this direction. Instead of going in R2, it will start traveling towards A and B. So technically, if you notice, the value of R2 does not hold any significance. So we can actually cancel out that, because the entire current will now follow this path. So in the outer part of the circuit, the current will start flowing. So R2 can be cancelled out. So all we are left with is a resistance R1, which is in series connected to the 12-volt battery. So now from this, what we can calculate is the short circuit current. So let us calculate the short circuit current. So ISC would be equal to the voltage drop across R1, that will be equal to 12 divided by 3, that is 4 ampere. So this is the value of IN that we have calculated, which is coming as 4 ampere. Now we need to calculate the value of Rn. So to calculate the value of Rn, we have to remove the short terminals A and B so that they are open again, and replace the voltage source by its internal resistance, that is a short circuit shown in figure 5.22a. So in the next step, what we do is we short circuit the battery over here. So in that case, what is going to happen is the R1 will be present here, R2 will be present here, but in place of this circuit, this voltage battery here, we'll be replacing it by a short circuit wire. And now we have A and B as the terminal. So as you can see, R1 and R2 are in parallel to each other. So now we calculate the value of Rn. So the value of Rn will be, R1 and R2 are parallel to each other, so this would be R1 multiplied by R2 divided by R1 plus R2. Let us substitute the values here. So this is 3 multiplied by 9 divided by 3 plus 9. So 9 3s is 27, and this is 12. So when you calculate this, this comes out to be 2.25 ohms. So here we have calculated the value of Rn as well. Now all that is left is to draw the Norton's equivalent circuit. Now let us draw the Norton's equivalent circuit. Let us do that with a black pen. Okay, so first I will draw the terminal A. This is terminal A. Then I will draw the current element, and then I will draw the terminal B, and followed by the Norton's equivalent circuit. So the value of the current element would be 4 ampere and the value of the resistance would be 2.25 ohm, and this is the Norton circuit, Norton equivalent. So as you can see, we have reduced this big giant complex network. In fact, it was here. So we have reduced this complete circuit in a very simple format circuit like this. So I hope that this video was informative enough, and for more such videos, don't forget to subscribe to our YouTube channel. Thank you so much for watching.